Okay, today we have the multi-pressure evaporators, individual expansion valve, compound compression with plus intercooler, this X and Y, plus intercooler X, plus intercooler Y, refrigeration system. So this is another type of open type uh, intercooler. Open in the sense that the, the medium are mixed within the system, and at the same time there is an exchange of heat within the system. So we have the system is composed of the whole refrigeration system is composed of three evaporators of different temperatures, so they have different pressures. We have an individual expansion device, and this compressor ABC, uh, it is considered as compound compression because the refrigerant coming from evaporator A, B, and C uh, pass all of them to compressor A, B, and C. Let's say your compressor, your mass coming from evaporator A will pass to A and then later on pass to B, accompanied by mass in your evaporator B, and then will later on pass into compressor C. In your intercooler, there is also a mass entering here, which is what we call MX, and the other one here is MY. We are going to define this mass later on. So it is called compound compression because of the what I've said a while ago. All of these masses, mass A, mass B, mass C, as well as mass X and Y, will later on compress into compressor C. At this point, we have all of these masses are combined together, so we have here at this point after compressor C we have the mass total, including also this point now. After all of these masses of refrigerant pass through intercooler Y, we have also here mass total. Mass total is the summation of all of these masses, so mass A, mass B, mass C, mass Y, and mass X, and they are compressed all of them into compressor C. So it is called compound compression. So again, um, the solution or the solution technique is to start in the lower portion at evaporator A. Whenever you have this intercooler, you are going to solve the problem starting at the bottom, evaporator A and compressor A. So let us consider this as your point 1, point 2, this is point 3. Note that this one is saturated vapor. After compressed that, it is superheated vapor. When the superheated vapor refrigerant enters your intercooler X, it is submerged in the liquid. Somewhere along this point is wet mixture. So the combination of superheated vapor and the wet mixture enters in your intercooler X. Then all liquid settle at the bottom because it has weight, and it allows only saturated vapor to go up. That is why the defined inside the intercooler. Superheated vapor is submerged into the liquid as well as the wet mixture refrigerant also submerged in the liquid. This one is above the liquid line or above the refrigerant liquid line inside your intercooler X. This is what we call your flush intercooler, these two, plus intercooler X plus intercooler Y. And so therefore, you change superheated vapor once again into saturated vapor. And take note, after your evaporator, it is considered saturated vapor, including this one. So at this point, they have the same phase. After the evaporator, we have saturated vapor. After the intercooler, again, we have saturated vapor also. That is why when the refrigerant enters compressor B, it is, of course, saturated vapor. So since they have the same phase, then they have the same point. That is point 3 also. And this is also point 3. Because they have the same condition or phase of the refrigerant. Then desaturated vapor again enters compressor B. You compress that isotropically at point 4. So you change saturated vapor by isentropic compression into superheated vapor once again. Again, the superheated vapor once again enters intercooler Y, and all liquid settle at the bottom coming from this point, which is wet mixture also, and it allows only vapor to, these are vapor, go up and sucked by compressor C. So if this is for superheated vapor, after it going out to your intercooler Y, we have once again saturated vapor here at this point. And this line is also saturated vapor. So this is for, you consider this also as your 0.5 also. Okay, 0.5, 0.5, 0.5. Okay, and then you once again change that into superheated vapor. You enter your condenser, you reject the heat. After your condenser, it is saturated liquid. So if this is 5, this is also 5. This is 5 also. You enter that to compressor into 6. And to your, after your condenser is 7. Okay, all of these are 7. This is 7, 7, 7. And then you enter expansion device, expansion valve 1 or expansion valve C. You change this into wet mixture. Okay, so if that is 8 or 7, then this line, they have the same condition, which is wet mix, that is 0.8. So this 0.8, this point is also 0.8. Okay, again 7, enter expansion B. So this is 9. This is also 9. And then we have 10. So you have 10 points. Okay, that is your multi-pressure evaporators individual expansion device compound compression with plus intercooler X and intercooler Y, and then you have of course this compressor ABC. Okay, so that is the change of phase in your refrigeration system. Now let's move on to the diagram, the pH diagram. Okay, note that the pressure of your intercooler Y and intercooler X is also the pressure correspond to your evaporator 5 and evaporator -2. This one. This is after expansion device from 40 it reduced to 5. So this line is, all of these are 5 degrees Celsius. The pressure corresponds to 5 degrees Celsius. And note that the refrigerant entering intercooler Y is coming from the line of the evaporator C correspond to pressure at 5 degrees Celsius, this one. And it's also excited at this point with the same pressure correspond to evaporator 5. So the pressure involved in your intercooler Y is also the pressure correspond to the pressure at, at evaporator C, which correspond to the pressure at 5 degrees Celsius, as well as this one. So therefore, the pressure involved in your intercooler X or plus intercooler X is also the pressure correspond to evaporator B, which is pressure correspond to -2 degrees Celsius. So no need for you to compute this. Like before, the pressure of your intercooler is somewhat computed by using the square root of the pressure of your condenser against the and multiplied by the pressure of your evaporator. This time, you are not going to compute this because the pressure in your intercooler correspond also to the evaporator connected on the line where the intercooler is connected. Okay, this one. And so, because of the change of phase that I am discussing to you discussed to you a while ago, we are going to plot the change of phase using your pH diagram. So all in all, you have your 40, okay, pencil. This line we have 40, we have 5, we have -2, we have -7. So we have, all in all, we have 4 pressure line. So if we consider this line, this corresponds to your 40 degrees, and that is your condenser pressure. Next is your 5 degrees, -2, and -7 degrees. Starting from point 1, this one, this is saturated at -7 degrees Celsius, and if that is saturated vapor, then you are going to connect that here. So that is your point 1. You compress the refrigerant passing through a compressor A isentropically, then change your saturated vapor to superheated vapor. At what pressure? The pressure corresponds to intercooler X, which is pressure at -2 degrees Celsius. So you compress it, one, you compress it isentropically until it cross pressure correspond to -2. That one there. So that is your point 2. And then at point 2, you change superheated vapor to saturated vapor at constant pressure because intercooler is at constant pressure. Okay, so from superheated vapor, once again change into saturated correspond to this pressure line. So that is your point 3. So that is one function of your intercooler. Change superheated vapor into saturated vapor. Okay. And then at point 3, all of these are with the same saturated vapor condition will enter compressor B. And then you compress that into 4 to convert that once again to superheated vapor. So at point 3, you compress it isentropically until it cross pressure correspond to 5 degrees Celsius, like this one. Okay, so that is your point 4. Okay, and then your point 5, which is superheated vapor, once again enters in your intercooler Y, and then once again change it into saturated vapor at point 5. Okay, so from 4 it will go to 5. Yeah, something like that. That converts superheated vapor once again into saturated vapor at the pressure correspond to 5 degrees Celsius. And then this 0.5 as saturated vapor enters your compressor C, then you compress it once again into isentropically until it reaches pressure correspond to your condenser at 40 degrees Celsius. Okay, so this one to 0.6 at superheated vapor region. And then in your evaporator, you reject the heat so that after it will pass, after it passes to your condenser, it changes superheated vapor into saturated liquid. So this one, 0.6, by constant pressure line, it will existed at 0.7 as saturated liquid. Okay, this one, saturated liquid. Okay, and since we have individual expansion, so you have all of this. Expansion device has constant enthalpy process or isenthalpic process or throttling process. You just write line vertically downward until it crosses pressures correspond to your evaporator, 5, -2, and 7. Okay, just a straight line going down until it crosses evaporator pressure. So this is your 8. This one is your 8. And then this is your 9. This one is your 9. And then this is your 10. Okay, so that is the pH diagram correspond to your multi-pressure evaporator, individual expansion valve, compound compressor with flush intercooler refrigeration system. So this is the corresponding pH diagram for this system. Okay, so you have 10 points, then you have your 10 points here. Okay, then this, of course, all of these are equal to H7, H8, H9, H10. That's correspond to HF at 40 degrees Celsius. This one, of course, is H1 equal to HG at -7 degrees. H3 is equal to HG at -2 degrees. H5 is equal to HG at 5 degrees Celsius. You extend this line. Okay, so you have all the enthalpies. 246 by chart. So you are going to plot this into your chart. course, you need to have at least exact enthalpy as compared to my enthalpy, so that we have the same answer later on. But then you have only plus or minus 0.5 if you plot this, so that we don't have a much difference in our answer later on. Okay, so after you determine all of those enthalpies, then you proceed with the solution. Okay, you can easily determine the masses ABC, and at the same time you can compute the heat added in a usual way. Let's say for masses, for mass A, oh, let us consider also, let's say this is 60 tons, 80 tons, and 50 tons. So with their given capacity, you can easily determine mass A. Mass A is just equal to 3.5167 kilojoules second ton. Then we have 50 tons here, all over REA. Your REA is just H1 minus H10. This one. This is your REA. REB, REC. Okay? So that we have REA H1 minus H10. Okay, you have your mass A in kilogram per seconds. For mass B, we have 3.5167 kilojoules second ton, and we have 80 tons, okay, over REB. Your REB is just equal to 3 minus 9. 3 minus 9. This one also. 3 minus 9. So that is your REB. REA, REB, REC. Okay. So your REB just equal to H3, H9. Okay. Then C, 3.5167 kilojoules second ton. At C we have 60 tons over REC. REC is H5 minus H8. H5 minus H8. This one. 5, 8. Okay. H5 minus H8. So you have the three masses. Okay. You can now compute QAs. Your QAs. Your QAs such as QAA in your evaporator A, this one, you have QAA, this one is QAB, and this one is QAC. QAA simply mass A, REA, QAB, mass B, RE, B, QAC, mass C, REC.